Today, I would like to talk about some of my recent work with my collaborator, Heinz Walensky, on associative memory of structured knowledge. So the preprint is available on bioRxiv, and hopefully the full paper should be out shortly. So the motivation for this work is you could think of various types of structured knowledge as sets of associations between discrete items in their contexts. So for example, this could be a temporal sequence where you have different events occurring at different times, episodic memories where you have a collection of events occurring in different contexts, cognitive maps where you have landmarks occurring at different spatial locations, and semantic structures where you have words and their roles. And so an important thing here is that, for example, in this series of meals, here, the chicken at dinner is basically a contextual representation, so having chicken at dinner. But conversely, you could have had, the tacos for dinner and chicken at lunch. So basically, the representation for chicken kind of retains its meaning whether you have it at dinner or lunch. So that's quite important. So the question we are asking is, how can the structured knowledge be represented in neural circuits for robust and scalable computation, including storage and recall in long-term memory? So this was kind of a problem that hadn't really been discussed much in the neuroscience literature. So first, just talk about some various properties of neural representations. So the relevant level for talking about higher cognition seems to be the neural network. So rather than talking about the actions of individual neurons, we kind of think of a coarse-grained notion of a neuron, which is a system that takes its inputs and outputs some linear function of these inputs. And the cognition happens at the network level rather than at the single neuron level. So then you can think of basically the space of firing rates. And so the vector in that space is representing some distributed neural representation. So rather than looking at the firing of one neurons, we think of the firing of all of the neurons, and things like the trajectory in that space can be thought of as the dynamics. And moreover, you get basically notions of similarity between representations, associativity. So basically, the distance between representations as meaning something. They're robust to having some errors, and you also get some notion of geometry. So here you can think of variability of a stimuli as basically being some sort of manifold. So, so this is all good, but you kind of run into problems when you talk about basically representing relations in neural networks. So, given that the information is distributed throughout the entire network, it could even be that you have things that are encoded on in different regions of the brain. How can you represent relational knowledge or associations between these items in a neural network? And it's not obvious how to do that. You have to have certain basically operations as being privileged to represent relations between different items. So essentially, you can kind of translate this problem as how do you represent all of these things? So time, temporal sequences, cognitive maps, semantic structures, episodic memories. So maybe these all have something in common where they're kind of representations that are built of symbols. And how do you represent that in a neural network? So beforehand, it was thought that basically computation, in the brain was, or at least at the cognition level, it was all symbolic manipulation. And the fact that you have, this distributed activity in the hardware wasn't really relevant. You can kind of abstract that away. But since it's been realized that, since you have something represented in a distributed way, there are all the other properties of that I mentioned before, which are attractive. So you want to kind of be able to figure out how do you get both. So several people have basically proposed ways to have kind of symbolic representations using, in terms of these, given that the fact that these items are represented by distributed patterns of activity. So, the important thing is that it has to be incorporated into the fixed size of the neural network. So let's say if you have a cognitive map, which has, a certain number of different spatial locations, it should be able to represent that in the neural network, which is independent of the size of the number of locations that you have in your cognitive map. So people kind of propose to do this by adding some kind of binding operation by hand. So some of the proposals were binding by synchrony. So for example, if you have, let's say, basically Bill and the lover, so Bill is the object and lover is the role. If those two representations fire close together, then that's kind of a binding operation. So you see Bill in the context of being the lover. Then another proposition was using the tensor product. So you have basically a representation for Bill, a representation for lover, and you take the tensor product of the two, and you get a contextual representation of Bill as the lover. So that was proposed by Smolensky. And then later, several people proposed this idea of this vector symbolic architecture. And so this is basically taking the tensor product and performing some compression of this. So you basically get a contextual representation of Bill and the lover as still being the same dimensionality as each of the role in the context. So you don't increase the number of neurons to represent the context. So each of these proposals have various limitations. So the first is that it's kind of difficult to understand, for example, if you had many different roles for a single person, how you would kind of represent that by synchrony, and also how you would store something like that in long-term memory and get the timing correct. So the second one, the tensor product, scales very poorly. So like suppose you wanted to go to higher level, basically more hierarchical representations. Well, then, the number of neurons would keep increasing, and you would basically get to the point where you didn't have enough neurons in the brain. And then the last one has the issue that the representation is lossy. So since you're going to represent each association, you're going from two vectors with n neurons to another vector of n neurons, then you're obviously like losing information in the binding operation. But it turns out that this may not actually be that bad, because you would expect that some of these properties would come out in terms of limitation of human cognition. So we kind of consider a model of storing relational structures in memory where you can consider neural representations of objects as being some vector of activity. For example, this object could be an event in an episode, a landmark, a word. And then a second set of representations of attributes. So for example, the context of an episode, a discrete location, or a time, for example, a context like being lunch or dinner. And then a relational structure is a set of many associations. So for example, what I like to mention is, suppose you had a classroom of students, or you had multiple classrooms of different students, and each of the classrooms had kind of identical configurations of desks, and each student sat at a desk. So for example, A1 here would be a representation of the student Andy, and B1 would be the representation of his desk. So first off, you want to be able to somehow encode this whole classroom into a single vector, I'll call S hat. So somehow be able to represent the structure as a single vector. So the structure was just a collection of associative vectors as S hat. Then you want to figure out how to store these representations in memory. So the most important thing is you have many different classrooms you want to store in the same network. Ideally, you would want to have a number of classrooms, which is of the order of the number of neurons. And then the next step is, how do you come up with some partial cue that's related to the fact this is a relational structure in order to retrieve the classroom from memory? And then finally, you want to somehow be able to use this representation to do some computational tasks. So in this work, we focus on decoding, the object using the context as a query. So for example, let's say you have the representation for desk 1. You want to be able to decode the fact that Andy is sitting in this desk. So, for the encoding, basically, you can think of the object attribute pair being represented via some nonlinear binding operation. So the details of this binding operation could actually, it doesn't have to be as specific as I present, But in general, you can have do it through the collection of matrices for each element of this new vector you're trying to come up with. You're representing the contextual representation. So then, of course, from this binding operation, you have a vector A, which has n neurons, a vector B, which has n neurons, and you produce another vector, which also has n neurons. So then you can kind of sum everything together in working memory, and you come up with a representation of this whole classroom. So you have information loss in two areas. So in the binding operation, but also the fact that you're summing everything together. And if you have any interference between these different contextual representations, then that will come out when you create the structure. So now for the decoding, basically you want to be able to query the structure with whatever context that you're interested in looking at. And in doing this, you come up with a noisy estimate for whatever object is associated to this structure. And so in general, since we had a multiplicative binding operation, we could also come up with a multiplicative unbinding operation. So basically, to do this, you must have the binding and unbinding operations being approximate inverses. And generally, you can learn what these are from examples, but a simple choice, which has been discussed a lot in the psychological literature, is a holographic reduced representation. So here you choose the binding operation to be the circular convolution operation, and the unbinding operation to be the circular correlation operation. So it's worth mentioning that this basically causes the binding between A and B to be commutative. So if you bind A to B, that's also equal to binding B to A. However, if you switch these two operations, you can get asymmetric binding. So for example, A to B would not be equal to B to A, just given how you choose the binding and unbinding operations. So now, given that you actually accumulate quite a bit of noise during the decoding, you can think how could you possibly make something that's actually useful to use for later computations. So what you can do is you can think of if I store all the objects and their attributes separately in some other neural networks, so probably another associative memory, then we could basically use this noisy version to retrieve the full object. So for example, I have a noisy version of Andy. I put that as a queue in some other memory network, and I could come up with the full version of Andy. And so to basically upper bound the performance of this, we can just consider maximum likelihood estimation. So we have the representation of the noisy representation of Andy, and we choose the item in the dictionary that basically has the maximum overlap with Andy. And so now we can think of this decoding error in this maximum likelihood estimation. So what's the probability that I give you the noisy version of Andy, and I come up with the incorrect student. So it turns out that this decoding error depends on two features. So the signal to noise ratio and the size of the dictionary. So the signal to noise ratio is basically just determined by the variance, the signal, so the square of the overlap between the estimator and the correct item in the dictionary, and then the variance between the overlap of incorrect items. So just the average of all of that. And so as you see here, the size of the dictionary doesn't matter too much. What really matters is of the signal to noise ratio. And this is proportional to N over L. So as you keep on increasing the number of neurons, you can do better and better with decoding. So just a quick overview of memory and neural networks. So some things we desire to be useful properties are that memory is associative, meaning that you can retrieve a memory from partial cues, and also that it degrades gracefully and is tolerant to some level of noise. And so Hopfield had an insight that given n neurons and p memories that are just basically different vectors of neural activity, you could choose the synapses somehow so that these memories are a attractor of the dynamics of the neural network. So here, just at zero temperature, just using these dynamics, you can start the network in a state that's similar to the memory that you want to retrieve, and hopefully eventually evolving that dynamics, you'll reach the correct attractor. And so in this scheme, you can store a number of memories, which is linear in the number of neurons. So each memory here is a different attractor. And you can define some properties of the retrieval process. So first, the quality of retrieval can be defined as this order parameter, which is basically the overlap between the retrieve state and the desired memory that you want to retrieve. And then secondly, you can define a basin of attraction for each memory. So this is basically the overlap you need for the initial, for the queue that you basically initialize the network in to retrieve the correct memory without having any errors. So now I'll talk about how we can think of storing and retrieving the structures I mentioned earlier. So first, you can basically come up with the representations of the different structures by the binding operation. And now we want to store a P of them. So P being linear, the number of neurons inside this attractor neural network. So first, you basically do this in our simulations. We choose the holographic reduced representations as being the binding operation. And then what you can do is you can binarize the structure so that you can store many different structures as single attractors in this network. So the important thing is that the objects and attributes should be stored in other memory networks. So basically providing some dictionaries. And then to retrieve each item from the network, usually you think of having a noisy version of a pattern being a retrieval queue. Now here, it turns out that instead what you can do is you can see basically take a few of the relations of the structure and create kind of a little structure and use that as a retrieval queue. And so then, for the decoding, you can just directly take the memory that you've retrieved and use that for the decoding process. So here is just a schematic of basically the whole process. So you take the memory and you create this retrieval queue. You input that into the memory network with a binarized version. And then you come out with this memory that you've retrieved, use the context as a query, get a noisy version of the object you're looking for, put in the dictionary, and then you'll hopefully be able to get the correct object. So something I like to do is show a visualization of this process. So here you start with this classroom here, right? And you basically encode this structure as a single and binarize it as a single vector of neural activity. And then, of course, you might have many different classrooms. And so you basically encode all in the same way. You encode them in vectors and store all of them as attractors in this network. And then I take, the representations of Anne and Victor in their desks, and I use that and I create a retrieval queue that will put me, hopefully somewhere in the basin of attraction of this classroom that I want to retrieve. And then I run the dynamics, I retrieve some version of this memory. So it might be that you reach the correct attractor, you might have also reached a state nearby. And so technically you could have, some noise in the memory retrieved. And now I want to take the desk of, let's say, Martin here, who importantly is not included in the retrieval queue, and use that as a query to identify a noisy version of Martin, which will then be put in the dictionary where hopefully I'll get the correct version of Martin. So the fact that Martin is not in the retrieval queue is very important because it shows that basically you need the memory to be retrieved, or at least some similar state to the memory, to know anything about Martin in his desk. So now for the decoding after retrieval, decoding error depends on more parameters. So it depends on the size of the retrieval queue, the number of relations in the structure, the number of neurons, the memory load, so you can define that as P over N, and then the size of the dictionary. So just as summary, right here, I list all the key parameters so you can remember what they are. And so so here is basically the decoding error for different sizes of the queues. And here I include the original structure. And and the size of the relations and also the number of neurons for 2 different memory loads. And so you see here for lower values of L, basically all the lines kind of match up. And eventually you'll get to a size L where they kind of, for each of them, they diverge from the decoding error for the original structure. And that's because the memory at that point is not perfectly retrieved. But something that's important to notice is even though the decoding error, increases quite a bit if the memory is not, is corrupted in some sense, it's still way better than if you just randomly chose an item from the dictionary. And another thing you notice is if you decrease, if the error will decrease as you increase n, even though when in doing so in a fixed memory load, the number of memories you're storing also decreases. And so this is because even though you're not getting a better retrieval because you're still operating at the same memory load, the signal to noise ratio is increasing. And so that is basically driving your decoding error down. And so in general, you have 2 retrieval regimes. And you can see this by just looking at the signal to noise ratio and comparing it to the signal to noise ratio for the original structure. So here for 8,000 neurons, you see that, at different memory loads, that basically the signal to noise ratio for each size of the retrieval queue closely matches that for the original structure and then diverges at some critical size, which is basically you can represent as a fraction of the size of the retrieval queue to the number of relations in the full structure. And in this first regime, basically below this critical value of L0, just given the size of L, you have perfect retrieval, so perfect pattern completion. And so what this means is that if you think about random patterns, the initial overlap of the retrieval queue that you're creating, which is basically proportional to the square root of this fraction, lies in the basin of attraction of the memory. And so the second regime is when this doesn't happen. And in this case, you get imperfect retrieval, but as we see here, you still have a significant overlap with the memory that you're trying to retrieve. And somehow this is still useful for decoding. And so you can think of that here as, so you are starting this state and you end up outside of the basin of attraction, but you're still close enough to the full memory to somehow gain information about, for example, Martin, even though Martin was never in the retrieval queue. So this is it's still useful even if you don't converge the correct attractor. So this critical structure size can kind of be deduced by considering the retrieval statistics for fully random patterns. So usually when you think of a Hopfield network, you think of each memory as just being a random pattern. And since the way that you're encoding structures, just in this case, we're considering random vectors just to look at limitations of the capacity. It still looks random, even though it has some structure, given that you created the memory just from this binding operation and summing together all of these random patterns. So given that the basin of attraction size, you can kind of come up with basically this critical value of L as a function of the memory load you're at. Moreover, you can also figure out what is the average overlap that you achieve, even if you're outside of the basin of attraction. So here, basically the average overlap that you end up with is proportional to the square root of the fraction of relations you're using for the retrieval queue, but also with this factor which depends on the memory load. And as you see here, for low memory loads, this is much bigger than 1. So basically the overlap that you're getting after the retrieval is considerably bigger than the overlap you started with in the initial state. So now we can kind of put this all together and come up with a notion of capacity for this relational memory. So in this case, you can kind of do this by looking at the SNR, which is now a function of this overlap of the retrieved memory with the original structure you wanted to retrieve. And so if n is very large, the SNR that basically takes this form, with this parameter here, which depends on the memory load. And so this theoretical value, I think, is around 0.52. And you see all the lines for the different sizes of the structure, so the different number of neurons, the different retrieval queues all collapse onto each other. And you could see this for two different memory loads. And so the black line is a theoretical line you would get. And so this basically says that as long as n L0 over L squared is much bigger than 1, you should have a good performance in this memory system. So the decoding error should be relatively small. So what's important is that initially you need to have some kind of decorrelation of memories to have a high capacity, both in terms of the system of memories, but also in terms of the decoding from the retrieved structures. So you would think that the best way to do this would be to use the pseudo-inverse rule. So as well, remember, basically the capacity of the pseudo-inverse rule is alpha equals 1. So you basically do this by inserting this inverse correlation matrix of the patterns, and this decorrelates the different patterns. So as long as they're linearly independent, you can store n of them, or p equals n of them in the network. So an issue with this rule is that it's non-local and non-incremental. So you need to know the full correlation matrix for all the patterns before you can come up with the synaptic structure. But it turns out that you actually can come up with a local rule by expanding this inverse correlation, and this becomes local and incremental. So here, basically, the first term is the Hebb rule that you usually see for a hot field network. And if you add the second term, it becomes this Storky rule. So this decorrelation kind of puts the memories, decorrelates different memories, which will increase the capacity. And if we look at the decoding error for the different learning rules, the pseudo-inverse and Storky rules are very close together, which is quite attractive. The Hebb rule does quite a bit worse, but it can still do considerably well at lower memory loads. So now we can basically think more about how you can store temporal sequences in this manner. So initially, a while back, people thought about storing temporal sequences as sequences of attractors. So basically, you could start in a retrieval queue that would get you to the first item in the sequence, and then the dynamics, adding some kind of asymmetric synapses would basically push you between the different attractors. So you start here, you go to the next attractor, and the next one, until eventually you end at the last item in the sequence. However, this is unattractive for two reasons. The first being that you don't have information about the whole sequence when you do this process. You only have information about which attractor that you're currently in. And secondly, the different sequences can't have overlapping elements. So for example, here, if you're trying to store this red sequence along with this blue sequence, and they both have this element in common, the dynamics won't be able to tell whether it should go to this item or this item. And you can see here in the average memory overlap, basically, this here is a result of this confusion over here. So a way to maybe improve this is to think about storing a temporal sequence as a single attractor in an attractor network. So to do this, you can think of temporal proximity as being kind of asymmetric context associations. So as I mentioned before, you could create a binding operation which is asymmetric, so that binding AL to B to AL plus 1, so the next item in the sequence is asymmetric. So if you reverse it, they're not equivalent. So then in a similar way, you can think of representing the sequence as the set of these associations and summing them together to create a representation of the sequence. And then you can basically store, binarize these representations and store all of them as single attractors in a neural network. And to retrieve them, for example, you can use the association between the first or second item as a retrieval queue. Alternatively, you could add, for example, the representation of the first item into the trace, and you could also use that as a retrieval queue that would subsequently get you the full sequence. So now what you can do is kind of sequentially do a cleanup operation to decode the sequence. So here you can see you encode all of these items in the sequence and store it in memory. And you use the first item as a query, do the unbinding, you get an estimate for the second item, you clean that up, use that as a query, get the next item, and so on until you get the last item in the sequence. So, so basically you can think about doing that, and it's attractive because the whole time you have the full representation of the temporal sequence, not just the current item that you're looking at. So now, when you're doing this, basically what will happen is you get an accumulation of errors along the sequence. So what's important here is this is worse as the sequence is larger, and this is because the length of the sequence appears in the signal to noise ratio. However, even at relatively large memory loads, so here alpha equals 0.05, and you have, let's say, 2,500 neurons, you can still decode the items pretty well along the sequence. So, let's say for a sequence of size 18, even if you're at the last item, you're still able to basically decode it with higher than 95% accuracy. And the next thing that's very important is that overlapping items don't compete. So before, with this storing memories as single attractors, you had this phenomena where if you got to an overlapping item, you couldn't really proceed reliably in the dynamics to the next item in the sequence you wanted to retrieve. But here, if you look at basically this overlap with this correct item, and you have two different sequences. So let's say you start along the first sequence, and you have basically these sequence sequence, which includes this common item here. So here you reach the common item, but you can still proceed along the decoding. And this allows you to store multiple sequences and actually have multiple items in common for each sequence. So for here, basically, you create sequences which have this number LS items shared between the different sequences. So even if you have a very large number of sequences and they share a considerable fraction of items between them, you can still store them and recall them and decode them with pretty high accuracy. And this is because the different sequences are stored in different attractors. So this is quite interesting. And so basically, if you see here, a possibility is that you get, let's say, the first two items in the sequence are the same for different sequences. And so then if the retrieval queue is the same for different sequences, that can cause interference. But otherwise, given that the sequences are stored as a decorrelated way as different attractors, that's why the issue is not that big. So there's also a mention to me recently at a psychology conference that I attended, is that there might be a connection from this sequence model that I proposed to this context retrieval update model. So this was first kind of discussed in basically thinking of a sequence as a word, and the letters in that word, so typing those letters is basically kind of decoding the sequence. So like each of the keys, so the locations of the keys are basically found by comparing this current context that you accumulate as you decode to the stored context, so presumably in some sort of dictionary. So you kind of update the context by adding the representation of the chosen letter to the current context. So if you think of typing this word very, it starts to look similar to what we proposed for decoding the different sequences. So in summary, basically you can think of this relational memory in the dictionary as complementary memory systems. So this is kind of an analogy to episodic memory. And together, having this relational memory and the semantic memory allows you to store these relational structures and be able to interpret and decode them with very high accuracy, given that you have things stored in the semantic memory. You can store many structures which basically are compressed representations, given that they represent many relations which have, are each the same dimension of the structure you're trying to store. and still you can decode well using this dictionary. And so you would predict that in doing this, that when you recall the entire structure, you would have persistent activity representing that. And of course, you have the sequence. When you recall a sequence, it would be represented in a single attractor. And you would basically also get some kind of activity that would be resulting from decoding that sequence. And so you can also think, again, of locations in the brain that this model might represent. So for example, this dictionary could be in the cortex, the encoding and the integration could be in working memory, and the structure would probably be stored in the hippocampus. So some further questions are, how would you implement this multiplicative binding? And so it seems that perhaps this short-term synaptic plasticity could be used to kind of come up with a sort of multiplicative interactions between different representations. The next is, how would you store higher order relational structures? So presumably you could do it in the same manner, but the capacity probably would be quite reduced. How much so is still a question. And so then another thing is, could you compare the observed recall probabilities for sequences of items with psychometric experiments? Another interesting thing could also be looking at this memory palace phenomena, where people basically can memorize a lot of items by imagining some kind of location and placing the items in the different locations. So the question there would be that since you're kind of creating a cognitive map in this sense, maybe that's why you're able to have a lot better memory, just because just the way that you're representing the structure. And so the last thing is maybe there's some transfer of things of episodic memory to semantic memory. So basically adding new items to the dictionary. So it could be a question of how that would happen, for example. So, and so now I'd just like to thank my collaborator, Chaim Sampolinski, for being very inspiring and working on this project. Just my various funding sources, of course, Princeton, for giving me a lot of freedom to pursue my research while I've been there, and just in general to thank the organizers for inviting me to this to present my work at this venue. It's been an honor. So thank you.